Now that you've been introduced to the electric flux and Gauss's law in the previous video lesson, now let's get into some concepts related to electric flux. So, number one, know your units for electric flux. We've already given the symbol for electric flux. It's capital Phi. And we said that in a case like this, where the field is uniform and the area is flat, then it's easy to calculate the flux through that surface. It's just the dot product of the electric field and the area. And in this case, the area vector, remember we say the area as a vector is the magnitude of the area times the normal hat vector. Well, the angle between the two is 0 degrees in this case, so this just becomes EA. Anyhow, the units then must be newtons per coulomb multiplied by square meters, or we could say it's Newton meter squared per coulomb. Okay, so know your units for electric flux. By the way, if we just took a tiny little portion of the overall area, then we would refer to that as dA. So I guess really dA is a vector. Okay, so the amount of flux through that little bit of area would be d flux. And that would be equal to the electric field dot product with just that little bit of area vector. So total flux could be found by making several little patches of dA, essentially breaking up the total area into a bunch of pixelated bits of area, and our total flux could be found by adding it all up. For example, we might have a curved surface instead of a flat surface, but the same shape electric field. So the electric field is all uniform and passes through this curved surface pointing to the right. So to find the total flux in this case, it certainly would not just be the product of the electric field and the total surface area. And not true in this case. That's because the angle isn't 0 degrees for every little bit of the area. So here, the little bit of area vector points up and to the right, but the electric field that passes through that little portion of it points directly to the right. Because it's a dot product, and there's some angle theta, that means the flux through the top and bottom isn't as great as the amount of flux through the middle. Through the middle, the angle between the electric field and the area is closer to 0, and if we continued this curvature, in fact, we might have a little portion of area whose vector points that way, and the electric field points to the right, and that little bit of flux would be 0. Okay, so that brings us to the next point, or the next concept about electric flux, and that is that flux is a dot product. You can see that with this example. So in case number 1, the flux would be equal to just the magnitude of the electric field times the total area. In case number 3, the electric flux would be equal to 0. If there's a non-zero area, there's a non-zero electric field strength, but the angle between those vectors is 90 degrees. So when we say flux is a dot product, we say we can calculate the flux by taking the magnitude of the field times the total amount of area times the cosine of the angle between those two vectors. So that's exactly how we would calculate it. In case number 2. Okay, another note to make about electric flux is that it only depends, a net amount of flux, and let me add a little caveat here, through an enclosed surface. The net amount of flux through an enclosed surface only depends on the amount of charge enclosed by that surface. Now, what's the point of this? Well, number one, in these previous examples, here we don't have a closed surface. This is an open surface. Something like a cube would be a closed surface, okay? A complete sphere, I guess, would be a closed surface. So this is an open surface. These are all open surfaces. Here we want to talk about closed surfaces, and we'll be getting closer to the point of Gauss's law. So the net flux through any closed surface only depends on the amount of charge that's enclosed by that surface. So let's take, for example, the case of the cube, which is basically 6 of these. And what if there's some charge that resides outside of that cube? It's not on the inside. We know what the electric field looks like. Points radially outward in all directions. A lot of these field lines do not create for any flux. Let's show each and every surface here. There we go. So I can draw in some more field lines. I won't draw them all. So there's some inward flux on the left face of this cube. But these field lines are going to continue onward. Okay, and so there's some amount of flux out on the right face. The amount of flux in and the amount of flux out are equal to each other. And so the areas are the same for the right and for the left surfaces. The field intensity looks like it's weaker, but then again, there's a greater number of field lines, right? So the amount of inward flux and the amount of outward flux, see we have some inward flux on the left side, so there's a greater number of field lines on that left than there will be on the right, because this field line actually passes out through the top here, right? But it doesn't matter, we count for the top and the bottom as well, not just the left and the right side. No matter how we look at it, the total amount of inward flux and the total amount of outward flux are going to be equal to one another, so the net flux will be equal to 0. And that doesn't matter how many charges you put on the outside. Q1, Q2, and we can draw its field lines and show how they pass in. There may be a greater intensity of field lines at the top surface than the bottom surface, just because the bottom surface is farther away, so the field is getting weaker, but there's also some field that passes through the right side and some field that passes through the left face from this charge. No matter how you slice it, the amount of inward flux and outward flux due to this charge will also cancel out and be 0. And it doesn't matter what the shape is. It doesn't have to be a cube. We can imagine some odd shape like this, and several charges, Q number 1, Q number 2, Q3. We can picture all the electric field lines. And no matter how much detail you put into the picture, you're going to find that the total amount of inward flux and the total amount of outward flux are going to cancel each other out as long as the charges reside outside of the surface. But if the charge resides on the inside of that surface, now it's a different story. So there's a name for these completely enclosed surfaces, right? In most cases, it's an imaginary surface, but not always. We'll refer to these enclosed imaginary surfaces as Gaussian surfaces. Now let's picture a charge Q on the inside. Okay, this electric field line passes outward through the top face. That field line passes outward through the bottom face. This field line comes out through the left face. This field line comes out through the right face, and on we go. And so the net amount of flux is entirely outward. So that's the idea. Net flux only depends on the amount of charge enclosed. It doesn't depend on any amount of charge that resides on the outside of your Gaussian surface. So let's test this idea and see if you can answer the following question. In which of the four cases below is there the greatest amount of electric flux through the Gaussian surface shown? In which case do we have the greatest amount? Okay. So the idea being net flux only depends on the amount of charge enclosed. What does it not depend on? It does not depend on the shape of the Gaussian surface. Interesting. So if I had drawn a sphere instead of the cube, there's still the same overall amount of flux pointing outward. Now, how can we argue this one? Let's see. In the case of the cube, I would think that the electric field has greater intensity through the top surface of this cube than the intensity in this vicinity of our spherical shell, simply because this is closer to the charge, and so the electric field is stronger. But then again, the amount of area here is not as great as the amount of surface area here. In fact, we could make concentric spherical shells. We can ask the same sort of question. If that's our charge Q, in which case do you have the greatest strength of electric field? Gaussian surface 1, Gaussian surface 2, or Gaussian surface number 3? In which case is there the greatest strength electric field? Well, clearly the answer for that is through number 1. But if we change the question and say, in which case is there the greatest amount of flux, they're all the same. Remember that flux is equal to the strength of the electric field multiplied by the area. Well, the field is governed by Coulomb's law, right? We know that the electric field is proportional to 1 over r squared. Coulomb's law is an inverse squared law. But the surface area of a sphere is 4 pi r squared, or in other words, the area is proportional to r squared. So for sphere number 1, 2, and 3, the only thing that's changing is r is getting bigger and bigger. So as the electric field gets weaker and weaker the farther away we get, as the electric field strength is going down, the surface area of our Gaussian surface is going up, and so the amount of flux remains constant. It doesn't matter how large our Gaussian surface is, and it doesn't matter what shape it is, whether it's a cube, whether it's a sphere, whether it's some oddball shape. The only thing the flux depends on is what? The amount of charge enclosed. So I think we know the answer to this question. Which of the following situations is there the greatest amount of electric flux through the Gaussian surface? Clearly, all of them are equal because each one of these Gaussian surfaces encloses a charge of 7 microcoulombs. So how does this concept of flux even relate to Gauss's law? Well, remember, Gauss's law says that the total flux, and what I've just written here is a way of saying total flux. Watch carefully. I just changed it to now saying total flux through an enclosed surface. This says total flux through any surface. This is a way of saying total flux through an enclosed surface. And the total flux through an enclosed surface is not just proportional to the amount of charge inside. We can say that it's equal to the amount of charge enclosed divided by a constant. Okay, well, Gauss's law is only practical when this integral is easy to evaluate. So there's a couple things that'll make this integral easy to evaluate. One thing would be if we can change it from being a dot product to a, I don't know, I'll just call it a simple product. In other words, if we don't have to account for this term, right? If we can make it that theta is equal to 0 for every element dA, it's just a lot easier to do scalar math than it is vector math. So that's one way to make the left side of the equation that represents Gauss's law easy to evaluate. If we can choose a Gaussian surface so that our angle will always be 0 degrees. Another way that would make it easy to evaluate is if we could take the electric field and pull it out of the integral sign. But that's only true if the electric field is uniform or constant across our entire Gaussian surface. So basically what we want is to take the left side of that equation and in step number 2, simplify it a little bit and just change it to E dA. In other words, get rid of the vector notation because we set it up so that the angle is 0. This means the geometry has to be right. The symmetry has to be right. Gauss's law is not practical in all situations, but is practical in situations where we can create a symmetry between the charge distribution and the Gaussian surface that we imagine to enclose it. In step number 3, we'd like to be able to take the E out of the integral sign. Well, if that's the case, this is always a simple integral to evaluate. The total surface area of an enclosed surface is just equal to total area, A. And so what happens if we do this well, if we find situations where we make it practical, then the left side of the equation for Gauss's law just says the electric field multiplied by the area of our Gaussian surface, right? The total surface area of our Gaussian surface is equal to Q in over epsilon naught. So we'll get there. I'll show you some examples of what I'm talking about. But for now, this is just a very important conceptual note to make about Gauss's law. So let's test this one. So here's a question. In which one of the following cases would it be impractical to apply Gauss's law? Let's say we had a sphere that was uniformly charged, but it's made out of plastic, right? So we say a uniformly charged insulator as opposed to a uniformly charged conductor. And maybe it's positively charged, and we want to find the strength of the electric field at point P. Well, we can make a Gaussian surface that's in the shape of a sphere concentric with the charge, and then we picture the electric field lines, and we notice that if we made a little patchwork of area, a bunch of little portions of the total surface area of our Gaussian surface, each one we label as dA, the electric field lines are going to pass through each of those dA so that the angle between those area vectors and the electric field is going to be 0 degrees in every case. That's just because our Gaussian surface happens to be concentric. Now, if we had made a situation where we have a charge Q and we use a sphere as a Gaussian surface, but it's not concentric with it, and maybe we're trying to find the electric field at this point P, okay, well, the electric field that passes through that little element of area forms an angle of 0 degrees with the area vector. But here, area vector for this little patch points in that direction, right? It lines up with the center of the Gaussian surface, but the electric field points at a different angle, and so the angle here is definitely not 0 degrees, and so it's going to make it tricky to evaluate the left side of the expression in Gauss's law, because we will not be able to get rid of the dot product, the vector notation. Okay. Likewise, if it was a conductor instead of an insulator, it doesn't change the idea here. It's probably wise to choose a sphere concentric with our charged conductor. Now, what if we chose a cube, by the way? What if I have a spherical charge and I imagine a cube as my Gaussian surface? Well, then we get the same problem. Now, this time the cube is concentric with the charge, but the electric field is not going to be at an angle of 0 degrees with the little area vectors in every case. Now, for this little area vector, yeah, the angle between that little area vector and the electric field is 0. But let's draw in this electric field line. Right? See the problem? The area that it passes through, that area vector points straight up, but the electric field points at an angle, so we've got a problem here. So generally, the shape of your Gaussian surface is very nearly going to mirror the shape of the charge that's creating the electric field that you want to solve for. So if we skip over question C and look at D, if we have a uniformly charged plastic rod and we want to find the electric field at the indicated point P, then we can make a Gaussian surface in the shape of a larger cylinder. If we break that up into little pixels of area, we notice the electric field and the area vector are parallel in all cases. And so it's going to make it easy for us to change E dot dA into just EdA. Oh, and by the way, the electric field, I should continue to draw it here. It comes this way out of our charged insulator. As we get to the ends, the electric field starts to curve. We have these fringe effects out near the end. But notice I was clever about my Gaussian surface. I didn't draw the Gaussian surface all the way down. My Gaussian surface didn't have the same length as the rod. If it did, we'd have this same problem again. The electric field is pointing at an angle, and the area vector is pointing straight up, and so the angle is non-zero, but we can outsmart it and just choose to make the length of our Gaussian surface to stay in the region where the field is uniform, so that none of the field lines that curve are going to create this problem. So I think you'd be stuck trying to find a Gaussian surface that could determine what would be the electric field at this point P if we had some uniformly charged cone shape. Okay, you might think, well, that should be easy. Let's just take this cone of charge. Okay, so this is like a solid piece of plastic in the shape of a cone that's been rubbed with fur or something like that. We're trying to find the electric field right here. Why can't I just make a larger cone as my Gaussian surface and use that to figure out the electric field at this point? I'm not sure that the field lines are really going to be perpendicular in all cases. Let me illustrate this. Maybe a cone isn't the best shape to illustrate this idea. Let's say we replaced the object in part C. Let's say it was a cube of charge. Again, for a cube in case A, great, you could apply Gauss's law. Case B, yep, even case D, you can apply Gauss's law. But in case C, whether it's a cone or a cube, no bueno. We can't do it. So think of it like this. This is our plastic cube that's been charged up. And you might have the inclination that you can just choose then a big cube as your Gaussian surface. And that ought to work out. Well, the electric field that comes out of here will point radially outward in all directions. Hey, so far so good. If I break this up into little patchwork, that little bit of area and the electric field are parallel. It seems like maybe this is going to work out. However, we know the electric field from here is going to start to curve outward like this. In fact, far afield, all the field lines, if I extend them, really are just going to look as if viewed from a very large distance, right? From really far away, it's hard to even recognize that this is a cube and not a tiny little sphere. It starts to look like a little pinpoint, and the field lines will all look like they're just coming away from the center of charge. Anyway, this electric field line and this little bit of area are not at an angle of 0 degrees. So, like I say, Gauss's law is not practical in all situations. And it's going to take some trial and error and some practice on your part to recognize when it is practical and when it's not. But generally speaking, we're going to apply Gauss's law most often to spherical shapes. Now, whether it's a solid sphere or a hollow sphere, whether that sphere is made of plastic and is insulating or made out of metal and conducting, in all those cases, solid metal spheres, hollow metal spheres, solid plastic spheres, hollow plastic spheres, in all those cases we can apply Gauss's law. And whether we want to find the electric field at a point P that resides outside, or we want to find the electric field at a point P that resides inside, maybe we want to find the electric field at a point that resides within the thickness of the spherical shell. In any of those cases, we could use Gauss's law. If the charge is in the shape of some long rod, we can use Gauss's law, whether we want to figure it out for a point outside or a point inside. And we could probably even use Gauss's law to find what the electric field would be if we had a hollowed out, charged cylindrical shape. We can use Gauss's law to figure out what the electric field would be near a large sheet of charge. I don't think we can use Gauss's law to figure out what the electric field would be for this charged rod. It's just a portion of a circular arc. So, yes to Gauss's law, yes to Gauss's law, yes to Gauss's law, yes to Gauss's law, no. And I know what you might be thinking, why can't I just make a Gaussian surface that's a larger bent cylinder like this? Well, I'll leave it up to you to draw the electric field lines and consider the shape, and I think you'll be able to conclude that it wouldn't be easy to convert this mathematical language into this mathematical language. I don't think you go from step 1 to step 2 to step 3 for this shape. In which of the following situations is there the greatest amount of electric flux through the Gaussian surface? Okay, so remember, it looks like in every case we've chosen a good shape for a Gaussian surface. The charges are all spherical, and our Gaussian surfaces are all spherical and concentric with the charge. But this might be tough to figure out. So I get it. It's more charge in case A than it is in case B, but then again, It's a larger area at a greater distance of r. No, remember, Gauss's law tells us that the net electric flux through the surface, and that's all this whole expression is on the left side of the equation for Gauss's law. This is a way of saying net flux through the GS, net flux through the Gaussian surface, is equal to, well, on the right side of the equation, there's no symbol for radius. The size of our Gaussian surface doesn't matter. Area doesn't show up again, the shape. The only thing that's on the right side of the equation is just a universal constant. By the way, if I haven't told you yet, that constant is named the permittivity of free space, and it's equal to 8.85 times 10 to the negative 12 Coulomb squared per Newton meter squared. Multiplied by 1 over that constant multiplied by the amount of charge enclosed. That's all it depends on. And so we don't have to look at the size or the shape of our Gaussian surface. We just have to look at how much charge is enclosed. So in which case is there the greatest amount of electric flux? Well, it's the case in which there's the greatest amount of charge, and that's A. And by the way, the answer would be the same even if the problem was like this. We've got 11 microcoulombs, 6 microcoulombs, and 2 microcoulombs, and in case A, the Gaussian surface is this weird shape. In case B, the Gaussian surface is a cube, and in case C, the Gaussian surface is a sphere, but a sphere that's not concentric with the charge in question. Well, then you might say there's no way to answer it because we can't use Gauss's law. No, Gauss's law is true. It doesn't matter what the shape is. It's true that the net amount of flux through these Gaussian surfaces in every case is equal to the amount of charge enclosed divided by epsilon naught. It's just that it would be hard to calculate exactly what the electric field would be maybe at this point, because it's just going to be mathematically challenging to calculate that integral. But it doesn't mean this equation isn't valid, okay? So we don't use Gaussian surfaces of these weird oddball shapes because it makes it hard to calculate the left side of the equation. But choosing a bad Gaussian surface does not invalidate the equation that expresses Gauss's law. Okay, so as a final check for understanding, let's see if you can rank the 5 Gaussian surfaces shown in the image here on the left based on the total amount of flux through those Gaussian surfaces, starting from least to greatest. Give you some time to think about it. You can hit pause if you want to on this video and write down your answers. And when you have all your answers written down, unpause the video and see if you've got it right. Okay, well, welcome back. I'm sure everyone said that surface number 1 has the least amount of flux simply because it encloses the least amount of charge. Well, let's just make a list for all the other ones. Surface number 2, surface number 3, surface number 4, and surface number 5. And see if we can calculate what the net flux is. Well, it seems like we should calculate net flux by taking the dot product, but there's an easier way to calculate net flux. We'll use the right side of the equation for Gauss's law. We'll say the net flux is the charge in divided by epsilon naught. But epsilon naught just being a constant, all we're really doing is ranking how much charge is inside of the Gaussian surface. Notice sometimes I use the symbol QENC to say charge enclosed. Sometimes I say Q in to say charge inside. Same thing. Okay, so surface number 2 has -7 microcoulombs, +9, and +5, so a total of +14 and -7, so we have +7 microcoulombs enclosed. Surface number 3, +9 and +1 for a total positive of 10, but also -10, so 0. Surface number 4, +8, -7, so positive 1 microcoulomb, and then surface number 5. 5 plus 9 gives me 14, plus 1 gives me 15, plus 8 gives me 23, minus 10 gives me 13, minus 7 gives me positive 6. So it looks like the amount of flux through Gaussian surface number 1 and Gaussian surface number 3 are equal, and then followed by surface number 4, and then surface number 5, and finally surface number 2 with the greatest amount of flux. Well, that was a long video, lots of information. Bet